Welcome back to the 2PP podcast. For today's deep dive, we are looking at something that honestly feels like the holy grail of digital imaging. Imagine a camera that doesn't just, take a picture, but fundamentally signs reality at the speed of light.
It really is the kind of technology that makes you sit up and pay attention. We aren't talking about software patches or metadata tags here. We are talking about physics.
Right. And for you listening, those of you who live and breathe nanofabrication, this is a massive treat. We're getting into a paper called NOWA, which stands for Null-Space Optical Watermark.
Yeah.
But really, at its core, this is a story about two-photon polymerization. It's a story about how 2PP is moving from cool lab prototypes to potentially saving the internet from a total collapse of trust.
That sounds a bit dramatic, I know, but it is highly accurate. Look, we are facing a profound crisis of trust right now. Generative AI, diffusion models, deepfakes. We have basically reached a point where you cannot implicitly believe your own eyes anymore.
No, you really can't.
I think everyone remembers that deepfake video of Ukrainian President Volodymyr Zelensky back in 2022. Just to be clear, we are just looking at the technical impact of that event, not taking any political sides here.
Of course. The one where he was supposedly telling his troops to surrender.
Exactly. And, it was clumsy by today's standards, but it was a massive wake-up call for the industry. The tools to fabricate reality are getting better so much faster than the tools to detect those fabrications.
Right, and usually the industry solution is just, well, it's more AI. Fight the deepfake with a deepfake detector. Fight software with software.
Which is a losing battle.
Exactly. But the research we are covering today says to stop doing that. Stop trying to fix the problem in post-production. You have to fix it in the glass.
It proposes a camera that inherently fingerprints every single image it captures. But, and this is the absolute key for you listening, you cannot build this camera with traditional lens grinding.
Wow.
You can't even easily mold it. You absolutely need the specific 3D freeform capabilities of two-photon lithography to pull this off.
So let's unpack this system. It's called NOWA. What is the actual hardware that makes this happen? Because I know you all want the exact fabrication specs immediately.
Naturally. So the heart of the system is a phase mask. It's a hybrid optical-digital setup, but the physical component is a small transparent piece of fused silica. It's roughly 10 by 10 millimeters.
And this sits right at the pupil plane, right? The aperture stop of a standard camera lens.
Correct. Right in the aperture stop.
Okay, so it's a piece of glass in the lens, but obviously it's not just a flat window.
Far from it. And this is where the 2PP comes in. The researchers, Vargas and the team, they use a nanoscribe photonic professional GT system.
Classic workhorse.
Yeah, and they print it in dip-in liquid lithography mode, or DILL, using the objective dipped directly into the liquid photoresist.
Which resist did they go with? Because you and I both know that choice dictates a lot about the optical performance of the final print.
They used IP-DIP. And what's crucial here is that this wasn't just a random choice for high resolution. It was very specifically a refractive index play.
Because of the substrate.
Exactly. IP-DIP has a refractive index of approximately 1.52 at 550 nanometers.
Right, and for any non-optics nerds who might be tuning in, 1.52 is the magic number here, because it's an almost perfect match for the refractive index of the fused silica substrate itself.
Precisely. When you are printing an optical element directly onto a substrate, you want the incoming light to be modulated entirely by the shape of the 2PP print.
You don't want it bouncing off a boundary layer.
Right. You don't want it modulated by the boundary between the printed polymer and the glass base. By matching the index at 1.52, they minimize unwanted Fresnel reflections or scattering at that specific interface.
So it basically creates a completely seamless optical path. It's not a lens, then a layer of glue, then a mask. Optically, it acts like a single monolithic complex component.
That's exactly how it behaves. And in terms of precision, they used a 63x objective to focus the femtosecond laser. The height map of this phase mask was discretized into 6 layers, and the step heights were just 200 nanometers.
200 nanometers. I mean, we're talking about physical steps that are significantly smaller than a single wavelength of visible light.
Which is the exact scale required for precise phase modulation. But here is where the fabrication constraint gets really interesting from a 2PP perspective.
The topography issue.
Yeah. If you want to scramble an image to hide a watermark, your instinct, or at least a software engineer's instinct, might be to just print random noise, just a completely chaotic surface profile.
Right, like static on an old TV screen, but translated into 3D heights.
Exactly. But you know as well as I do that you cannot simply print pure high-frequency random noise with a 2pp system.
No, it would be a disaster.
If the digital design demands that the laser jump from 0 height to maximum height pixel by pixel, you get a structural nightmare.
The aspect ratios would be impossible to maintain. You'd have microscopic polymer pillars falling over, uncross-linked resin getting permanently trapped in the crevices.
And catastrophic shrinkage during development.
Exactly.
It's just not manufacturable. It would scatter light completely unpredictably and probably just collapse off the substrate. So the researchers had to design a surface that was optically complex enough to scramble light, but mechanically smooth enough to survive the printing process.
And that is why they use Zernike polynomials.
Yes.
Now, I usually hear Zernike polynomials when an optometrist is explaining why my eyesight is terrible. They describe optical aberrations, right?
They do. Astigmatism, coma, spherical aberration, those are all mathematically described by Zernike polynomials.
Right.
But here, the researchers basically use them as a topographical design language. Because Zernike polynomials are inherently continuous and mathematically smooth, using them guarantees that the resulting printed topography is going to be incredibly print-friendly.
So they essentially designed a perfectly smooth, deliberate distortion.
That's a fantastic way to put it. They deeply respected the mechanical and optical constraints of the nanoscribe to create a surface that bends light in a very specific, calculated, and most importantly, stable way.
And how did they actually mount it?
They did a bit of DIY lens surgery. They hacked a commercial lens, a young NOWA 50mm f1.8 to be exact. They fully disassembled it, cut the fused silica substrate to fit, and literally used carbon tape to mount this 2pp printed mask right at the physical aperture stop.
I just love that mental image. You have this state-of-the-art sub-micron nanofabrication, and it's being held in place by carbon tape in a disassembled $50 lens.
Sometimes the simplest integration is the best.
So true. So we have this mask in place, light comes into the lens, hits these 200 nanometer printed steps, and gets phase shifted. Now we have to talk about the physics side of this. The paper focuses heavily on the concept of the null space.
Yes, this is the entire core of the concept.
To me, null space sounds like a dimension in a sci-fi movie where bad scripts go to die. What does it actually mean in the strict context of imaging?
Think of it this way. Every single optical system has a blind spot. And I don't mean a physical blind spot in your peripheral vision or a blockage in the lens mirror. I mean a fundamental mathematical blind spot.
Okay, walk us through that.
If you think of capturing a photo as a linear algebra equation, where the incoming light field multiplied by the optical operator of the lens equals the final image on the sensor, the null space is the specific set of all light inputs that result in exactly 0 on the sensor.
0?
Yes. The camera literally cannot see information that falls into the null space. It gets completely annihilated by the mathematical physics of the lens.
So if the camera physically cannot see it, how on earth do we use it to embed a watermark? Logic would dictate that if you purposefully put your data in the blind spot, it's just gone forever.
And that right there is the brilliant trick.
Yeah.
The 2pp phase mask is mathematically designed to manipulate that exact null space. It takes a specific watermark pattern, the NOWA signature, and it embeds it purely into this unobservable subspace.
I am still struggling a bit with the word unobservable here. If I pick up this heavily modified camera and I take a picture of you right now, what do I actually see? Do I see the watermark floating over your face?
In the final processed image, no, absolutely not. It is completely invisible to the human eye. But in the raw image, the actual photon counts coming straight off the CMOS sensor, the mask creates a very specific, intense type of blur.
Oh, so the raw image is degraded.
Highly degraded. It looks like a severe optical aberration.
So if I buy this highly secure cryptographic camera, my raw photos look completely out of focus.
They look fundamentally broken. Honestly, they look like you smear a thick layer of Vaseline directly onto the glass.
Well, that seems incredibly marketable. Buy our new camera, the photos look absolutely terrible.
Right, but that's exactly where the second half of this architecture comes into play. You have to remember this is a hybrid system. You have the physical 2pp hardware modifying the light, and then you have the digital null space network, or NSN, processing the result.
Is that NSN just a fancy academic name for AI upscaling? Because my television does that, and it makes every movie look like it's starring wax figures.
It is significantly more sophisticated than your standard AI upscaler. Standard sharpening AI just hallucinates high-frequency details to make soft edges look crisp. It guesses.
Right, it invents pixels based on its training data.
Exactly. But the null-space network acts as a digital lens. It is strictly trained to be measurement consistent.
Meaning what exactly in this context?
Meaning it takes that raw, physically encoded, highly blurry data from the sensor and reconstructs in a mathematically sharp, high-quality image. But, and this is the absolute crux of the paper, it restores the semantic image while strictly preserving the invisible null-space watermark.
I see. So the 2PP hardware purposely breaks the incoming light in a mathematically specific way, and the software fixes the visual part of the image, but deliberately leaves the underlying cryptographic fingerprint completely intact.
Exactly. And the reason this works so well is that they are co-designed. This isn't hardware first, software second.
It's end-to-end optimization.
Yes. The optical parameters, meaning the specific physical shape and Zernike coefficients of the 2PP mask, and the digital parameters, the neural network weights, are learned jointly. They co-evolved simultaneously in the training simulation before anything was ever printed.
Which means you absolutely cannot swap them out. You can't take the NSN software and use it to decode an image from a different lens.
Correct. And that creates a massive fundamental security asymmetry. To forge this specific signature, an attacker would need two distinct things. First, they obviously need the fully trained neural network weights.
Which might be stealable in a software hack.
Sure. But second, they would need the exact physical 2PP mask with those highly specific Zernike surface parameters.
And since that mask was custom printed with 200 nanometer layer precision, good luck trying to file a piece of plastic down by hand to perfectly match it.
Exactly. You physically cannot generate a mathematically valid NOWA signature without the exact piece of hardware that creates that specific light projection in the real world.
Okay, so let's play red team for a second. Let's really test the limits of this. I'm a bad actor. I do not have the physical 2PP mask, but I managed to get my hands on a high-resolution photo taken by this verified camera.
Okay, you have an authentic signed image.
Yes, and I want to fake a major news story. So I take that authentic photo into Photoshop, and I use generative fill to seamlessly remove a prominent person from the background. Or maybe I completely swap a face. How does the NOWA system actually catch me?
This is where the physics bites back. To verify the image, the security system doesn't just look at the pixels on a screen, it computationally projects the image back into the null space.
It looks directly into the blind spot.
It does. For an authentic image, meaning one where every single pixel actually passed through the 2PP mask, that revised projection reveals a perfectly consistent, predictable signature map. It's essentially a mathematical secret handshake between the captured pixels and the physical lens optics.
And for my maliciously faked pixels, the ones that generative AI invented out of thin air.
They don't know the handshake. The new pixels you generated with Stable Diffusion or Photoshop might look hyper-realistic to the human eye, but they fundamentally do not respect the strict mathematical constraints of the phase mask.
So they just completely stand out.
Like a massive beacon. When the verification network generates a signature map, the authentic, untouched parts of the photo look like a smooth, consistent layer of noise. But the tampered parts, the face you swapped, the specific person you erased, they completely light up on the map. The detector network localizes the tampering on a pixel-by-pixel basis.
I really want to talk about the concrete numbers here.
Yeah.
Because we can detect deepfakes as a claim I see in startup press releases literally every single week.
Oh, absolutely.
And usually it works 80% of the time on one highly specific, clean data set and then fails miserably in the messy real world. How did NOWA actually perform in their tests?
The quantitative results were incredibly strong. They benchmarked it directly against state-of-the-art purely digital methods. One of the top competitors right now is a method called EditGuard.
Okay, and how did EditGuard do?
EditGuard, which again is purely software-based, had an F1 score of 0.966.
Which honestly is already pretty high for tamper detection.
It is very respectable. But NWA achieved an F1 score of 0.993.
Wow.
And you know that in the world of cryptographic security, closing that final gap from 96 to over 99% is a massive, massive hurdle. It effectively means almost zero false positives and almost zero misdetections across their data set.
And this actually worked against the big modern generation tools, things like Stable Diffusion and ControlNet.
Yes. It reliably detected edits from Stable Diffusion, ControlNet, SDXL, all the current heavy hitters in the generative space.
Yeah.
But there is another layer to this that I think is even more critical for any actual practical application, and that is the balance between robustness and fragility.
I'm glad you brought that up. Unpack that distinction for everyone.
Think about how you actually use digital photos. You take a picture, you upload it to a social media platform. Those platforms heavily compress the file to save server space. They resize it. You absolutely want the security watermark to survive that normal pipeline. That characteristic is called robustness.
Right, because if the cryptographic watermark completely disappears just because I saved the file as a level 8 JPEG, the entire system is completely useless for everyday journalism.
Exactly. And the NOWA is highly robust in that regard. It survives heavy JPEG compression down to a quality level of 70. It survives standard Gaussian noise injection. It survives the normal wear and tear of the internet. But crucially, you also want fragility.
Fragility. Now, usually in security engineering, fragility is a bad word.
Usually, yes. But in the specific context of tamper detection, it's exactly what you want. You want the watermark to be highly fragile, specifically when the actual semantic content of the image changes. If I maliciously change a cat in the photo to a dog, I want the watermark in those altered pixels to break immediately and loudly.
I see. So you resize the entire image uniformly. The watermark survives. You remove a specific person from the frame. The watermark completely breaks in that localized area.
Precisely. And achieving that exact balance is notoriously difficult with purely digital watermarking methods.
Because software struggles to distinguish between harmless compression artifacts and malicious semantic changes.
Exactly. But because NOWA relies on the inherent physical consistency of how light propagates through the 2PP mask, it handles this balance completely naturally. Standard compression doesn't change the underlying optical physics of the captured scene, but an AI-generated edit introduces pixels that never pass through that optical path.
So the physics inherently flags it. Now, did they actually build this full pipeline? No offense to optical engineers, but a lot of these computational optics papers are just really elegant computer simulations.
No, they absolutely built it in the real world. As we mentioned, they used a Canon EOS 5D Mark IV equipped with that surgically modified young NOWA lens.
The carbon Tate special.
Exactly. And for the experiment, they displayed highly controlled scenes on a high-resolution LCD monitor to ensure they had a perfect ground truth. They captured those scenes through the 2PP mask, and then they maliciously attacked their own physical photos using Adobe Photoshop's generative fill.
And the software detector worked flawlessly on the physical prototype images.
It did. It successfully distinguished between the real optical signature embedded by the glass and the AI-generated fill layered on top. It wasn't just a MATLAB simulation.
That is just wild to think about. It's literally like the camera lens leaves a microscopic DNA sample on every single authentic pixel, and the AI paste just fundamentally doesn't have the matching DNA.
That's a practically perfect analogy for what is happening mathematically. And they didn't stop at just simple generative edits. They ran rigorous adversarial tests. For example, they tried a camera imitation attack.
What exactly does that entail?
Basically, the attackers train a separate neural network to deeply learn the specific visual style of the target camera. The attacker's AI says, well, this camera blurs the edges in this exact way, and it introduces this specific color shift. So let's try to perfectly mimic that exact style to fake the signature.
It's like an art forger trying to mathematically perfectly forge a master painter's unique brushstrokes. Did it work against NOW?
It completely failed, because the attacking AI fundamentally cannot reproduce the deep null-space correlations without passing light through the actual physical mask. They even tried blind deconvolution.
Which is what, trying to mathematically guess the point spread function?
Exactly. Trying to guess the exact point spread function of the lens to reverse engineer the mask's topography from the blurry images. That failed completely too.
It really just highlights the raw power of moving security to the hardware layer. We spend so much time and billions of dollars worrying about software vulnerabilities, but here, the core security is literally baked into the physical topography of the lens itself.
And this brings us right back to why this is such a quintessential application for two-photon lithography. Think about the strict physical requirements we just listed out today.
Right.
You need a custom, perfectly refractive surface. It needs to be merely microns thick. It needs to be flawlessly utilizing those Zernike polynomials to avoid any stray light scattering. And it needs to be perfectly integrated into a tiny, very specific spatial plane inside a commercial lens barrel.
Yeah, traditional UV lithography, the kind they use for making silicon chips, it just can't do these continuous, sweeping, curved 3D shapes easily without insane grayscale mask costs.
And precision diamond turning is way too slow and vastly too expensive for this scale and complexity.
Exactly. Two-photon lithography is arguably the only viable way to prototype and develop this technology effectively. It basically turns a standard 2pp machine into a printing press for digital trust. So looking forward, let's talk scale. We have a working prototype on a bulky Canon 5D DSLR, but the real problem with misinformation isn't usually professional photographers with DSLRs, it's billions of people with smartphones. That's where the fake news spreads. Can we actually shrink this system down to fit in an iPhone?
That is undeniably the logical next step for the field. The 2pp mask is already at the millimeter scale, so size isn't the primary blocker. The main challenge right now is sheer fabrication speed.
Volume.
Right. We know 2pp systems are getting much, much faster with things like multi-beam and advanced scanning, but directly printing hundreds of millions of these individual masks for every single smartphone camera assembly is a very tall order right now.
Unless you change the manufacturing paradigm.
Exactly. Unless you use 2pp solely to master the molds. You print the perfect submicron averse of the phase mask using the nanoscribe, and then you use something like nano-imprint lithography NIL to stamp them out of optical polymer by the millions.
Boom. There's your viable global supply chain.
The path to integrating this into the standard smartphone camera stack is definitely there, and so what here is just massive for society. This technology offers a very real path to verifying not just copyright ownership, which is where digital watermarking usually lives and dies, but verifying the actual reality of the scene itself.
It fundamentally changes the burden of proof for digital media.
It physically proves an image came from a specific physical device in the real world and hasn't been structurally altered by an AI. Imagine a photojournalist working in a war zone. If their camera stack includes a nano-ID mask, every image they capture has an unbreakable cryptographic chain of custody from the exact moment the photons hit the CMOS sensor.
It creates what you might call a structural security asymmetry. The defender, the person who owns the authentic camera, they have the physics on their side. The attacker only has the pixels. And in that fight, physics wins every time.
And it beautifully solves the age-old problem of spoofing raw data. Even if a highly skilled hacker completely compromised the camera's internal software to falsely flag a generated image as real, they still couldn't fake the underlying optical signature because the physical light simply never passed through that specific piece of polymer.
I have a final thought about where this naturally leads us. We are all very used to seeing standard metadata on our photos, right? The date, the time, the GPS location. But if this 2pp technology scales via nano-imprint lithography, could we realistically see a near future where major social media platforms or international news agencies strictly require metadata to be inherently signed by a physical phase mask? We might be rapidly entering an era where if an uploaded image doesn't have a verifiable physical shadow resting in the null space, it simply isn't trusted by the algorithm. It's just flagged as unverified AI slop by default.
I think that is a very distinct and necessary possibility. We might look back at this current era of computationally unsigned, easily manipulated images as the absolute Wild West of the internet. The future of absolute truth might literally need to be printed directly into the lens.
A truly fascinating look at how deep nanofabrication, specifically two-photon polymerization, could genuinely step up to save the foundational trust of the internet. A huge thanks to the research teams at Rice University and Universidad Industrial de Santander for publishing this incredible work.
Yes, it is always incredibly rewarding to see 2pp stepping out of the material science lab and directly solving massive real-world global problems.
And thanks to you for breaking down the complex optical math for us today. For you listening, think about how your own 2pp structures might interface with computational algorithms. We will catch you on the next deep dive.